NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everyone. My name is Gregory Smith from Jet Propulsion Laboratory's Communications and Education Directorate, and I'm so excited to be your host for this edition of the Von Karman series. Tonight, we'll be diving into our solar system's ocean worlds. See what I did there? Follow the water has long been the mantra of astrobiologists in search of life in the universe, as H2O remains the fundamental building block of all life as we know it. NASA missions have discovered evidence of liquid water throughout our solar system. So tonight, we'll discuss what the future of space exploration to these worlds might look at. To sort through the multiple questions we hope to receive from you, our viewers, we have my fearless co-host, Solar System Public Engagement Lead here at JPL, Lawrence Fauconnet. Hi, Lawrence.
Hey, Greg, and hey, everybody. I will be handling the Q&A portion of our program tonight, and we are so excited to read all of your questions about ocean worlds. Our social media team will be working behind the scenes to pull up questions from all of you on LinkedIn, X, and YouTube. If you're on one of those platforms and you don't see a way to ask a question, try refreshing your browser and a Q&A box should pop up. Throughout tonight's presentation, I'll field some of your questions to our two speakers. We won't have time to answer all of them, but we'll answer as many as we can in the time provided. We want to hear from you. This is your space program. Back to you, Greg.
Thanks so much, Lawrence. We have two fantastic speakers tonight. My first is NASA JPL planetary geologist and Europa Clipper project staff scientist, Dr. Cynthia Phillips. Welcome, Cynthia.
Thanks, Greg. So happy to be here.
And next we'll be chatting with JPL robotics technologist, Dr. Benjamin Hockman. Thanks for joining us, Ben.
Thanks, really excited to be here.
We'll be back to chat with Ben later in the program. So Cynthia, let's begin with you. What defines an ocean world and where might we find them in our solar system?
Thanks, Greg. So when we think of an ocean world, we usually think of a world like the Earth. And the Earth has a metallic core in the middle, then we have a rocky layer on top of that, and then our nice ocean of liquid water. And on top of that ocean is an atmosphere, and then atmosphere helps to protect our ocean and insulate it from the vacuum of space. And so when we originally thought about worlds that could be habitable, we thought of worlds like the Earth. But what we found as we've started to explore our solar system is that there's a different kind of ocean world that's here in our very own solar system. And these are ocean worlds like Jupiter's moon, Europa. And so Europa is a moon, it's about the same size as Earth's moon, but Europa actually has an ocean of liquid water underneath an ice layer. And so what we see on Europa is an ice layer at the surface, we see an ocean of liquid water, and then under that ocean, in the next slide, you see that there's a rocky layer and a metallic layer. So it's just like the interior of Earth, except that you have an ice layer on the surface. And so basically, if we move on to the next, we found multiple worlds like Europa in not just in our solar system that have this ice layer at the surface and then an ocean beneath it. And so next slide, please, will show us that we have worlds in the Jupiter system, so we have not just Europa, but also Ganymede and Callisto, we think have oceans below their icy surfaces. In the Saturn system, we have the large moon Titan, and then the tiny moons Mimas and Enceladus, we also think have subsurface oceans. Out in the Uranus system, we have Ariel, Umbriel, Titania, and Oberon, which are suspected to have subsurface oceans. Out in the Neptune system, we have Triton, and we even have some dwarf planets like Pluto and Charon, and Ceres, which we also think could have subsurface oceans below a surface ice layer.
How did scientists discover that there are oceans below these surfaces?
Next slide, please. So the story of the ocean on Europa is really a detective story. So basically, what we knew from ground-based telescopes back in the 1970s was that the composition of Europa's surface was predominantly water ice. So we knew that that icy composition was there, and we knew that Europa was actually one of the brightest objects in our solar system. What we found when we actually flew past Europa using first the Voyager spacecraft in the late 1970s was we found a surface that was covered with these strange, long, linear features, and we saw very few impact craters on the surface. And craters are used like a kind of planetary clock. The more craters something has, the older the surface is. Because if you don't have craters, craters are formed by impacts of comets and asteroids, and so they're kind of like a clock that accumulates over time. And so if there's something going on that world that can resurface it, then those craters can go away. So that's what we saw in Europa. We saw a young surface with very few craters. And so finally, with the Galileo spacecraft in the 1990s, we saw that the long linear features were actually cracks and there were ridges on the surface. We saw areas where the surface had broken apart into these disrupted chaos terrain blocks. And we were able to observe not just the geology with images, but with other instruments as well. And so one of the key instruments was actually our gravity and radio science experiment on the Galileo spacecraft that gave us that interior structure. That told us there was a layer at the surface about 100 kilometers thick that was made up of some portion probably of solid ice and some portion of liquid water. But actually it was the magnetometer on Galileo that measured a magnetic induction signature that we think came from a salty global ocean, a subsurface ocean. And so this magnetometer signal was one of our best bits of evidence that there actually was an ocean on Europa. And so next slide, please. What we found is that really there are two types of ocean worlds. So we think there are worlds like Europa and also Saturn's tiny moon Enceladus. Those are worlds that are similar to the Earth. And so in these worlds, you have that ocean layer on top of a rock layer. So that's important because that's what we have here on the Earth. And at the bottom of Earth's oceans, where that ocean layer touches the rock, you can have all sorts of interesting chemical reactions take place in hydrothermal systems. Whereas in worlds like Ganymede and Callisto and probably Titan, we think there is a subsurface ocean, but that ocean is sandwiched between two ice layers. You have ice at the surface, you have this water ocean, and then you have another layer of ice. It's probably a more high pressure version of ice. And so worlds like this are still really interesting, but they don't have that possibility for interaction with the ice layer with a rocky subsurface.
Fascinating. What do you think, Cynthia, what do you think the chances we might actually discover life in one of these oceans could be?
So next slide, please. So Europa, we think, has all the ingredients for life. And when I talk about life, I'm talking about life as we know it. So that's life like we have here on Earth. And that's not a failure of imagination. That's just because that's the only kind of life we know about. And so that's the only life that we really know how to look for. So life here on Earth, it requires liquid water. And so this ocean on Europa, we think it has more water than all of Earth's oceans combined. So that's plenty of water. And it's salty, but it's a little bit less salty than Earth's oceans. So in addition to water, we think you need the right chemical elements for life. And so these are fundamental building blocks like carbon, hydrogen, nitrogen, oxygen, sulfur, phosphorus. And these are elements that are common in the solar system. And so our models show that it's likely that they're abundant in Europa as well. And then another key component for life is a source of energy. So it would be really boring if you had all this ice and water sitting there, you have the right chemistry, but there's not enough energy to actually drive chemical reactions to help sustain life. And so in Europa, we think that there could be chemical reactions that could take place, like I said, at the bottom of that ocean, where it could interact with that potential hydrothermal systems. So it could circulate into that crust, it could have interesting chemical reactions, it could absorb some of that material and be heated. And then on Europa, there's another potential energy source, which actually is the surface. So Europa orbits Jupiter within its really strong magnetic field. And so the surface is fried by radiation. And so this radiation can create interesting oxidants and organics when it impacts the surface of Europa. And if these materials could then work their way through their ice layer into that ocean, they could also help to sustain the chemical reactions that we think could drive life. And then finally is stability. We think that this ocean has been there on Europa over the age of the solar system. So that's 4 billion years. So basically, if life was ever going to form on Europa, it had plenty of time to get going.
Incredible. Now, I know that you cannot wait to tell us all about JPL's upcoming mission to Europa.
That's right. I'm so excited. Next slide, please. So Europa Clipper is a mission we've been working on for here at JPL. We've been building it for about 9 years, but really we've been working on it for almost 25 years. We've been trying to get a mission to go back since the Galileo mission ended its observations in the Jupiter system. And so Europa Clipper is in Florida. It's headed to the launch pad next month. Our launch period opens on October 10th, and I am so excited to see what this mission will be able to do. So Europa Clipper is a huge solar-powered spacecraft. It's about as big as a basketball court from end to end of those giant solar arrays. And it has a suite of 10 science investigations. We'll orbit Jupiter. We'll have almost 50 close flybys of Europa. And on each of these flybys, we'll observe with cameras at various wavelengths from ultraviolet all the way out into the thermal infrared. We have a radar to help peek below that ice layer. We have a dust detector and a gas detector to measure the composition of particles thrown off the surface. And we have a gravity and radio science experiment and even a magnetometer to help to confirm that magnetic induction signature. So I just can't wait. And if you want to hear more about Europa Clipper, go to our website, which is go.nasa.gov/Europa Clipper to find out more and even find out how to watch that launch. It's going to be amazing.
Amazing. We are all such big fans of this mission, and the team has been incredible. And so we all here wish the Clipper team all the best of luck with the launch. Let's pause here and let's see if Lawrence has any viewer questions for Cynthia. Lawrence, what have you got for us?
We sure do. Questions are pouring in, so thank you. One question for Cynthia from Hello Universe on X. They are curious, where does all of this water come from?
Oh, that's a great question. So there's two different theories about where the water comes from. The most accepted one is that water was there when Europa formed. So we know that the satellites of Jupiter, they formed in kind of like a mini solar system surrounding Jupiter. And at the distance from the sun where the Jupiter system formed, this was kind of the place where the temperatures in that early solar nebula, when the solar system was forming, when the planets were forming, they were cool enough for gases to start to condense out. And so this is kind of the place, we sometimes call it the snow line, where it's the place where we first start getting things like the gases that go into the giant planet Jupiter, but also where we can start having hydrogen and oxygen, forming water, forming ice. So most of the moons of the outer solar system have a lot of ice, a lot of water in them. And so we think that likely that ice on Europa has been there since it formed. But another possibility too is that there could be some that was delivered from impacts of comets kind of over the age of Europa. So that could be another source, we think, for some of this water as well.
Great question. Lawrence, we're going to leave it there for now, but please keep sending in your viewer questions. We love them, and we will be back in a little bit for more Q&A with Lawrence. So Cynthia, after Europa, which ocean worlds might we be exploring next?
So the next slide shows Ganymede and Callisto, which are two other big moons in the Jupiter system. And so these are moons, like I mentioned before, where you have a surface ice layer, you have a liquid water ocean. So this ocean is further, it's deeper below the surface than it is on Europa. And then under that liquid layer, we think there's another layer of ice. And so next slide, these worlds will be explored with the JUICE mission, which was actually launched last year by the European Space Agency. And so we're really excited because Europa Clipper and JUICE are going to be in the Jupiter system at the same time, and they'll be able to make some really cool joint observations. JUICE is going to mostly focus on Ganymede, and that's actually going to go into orbit around Ganymede after doing some observations of the rest of the moons as well. And so next slide, please. So in addition to the Jupiter system, we also have the Saturn system. So out at Saturn, we have a big moon called Titan. And so you've probably heard that Titan's surface has these hydrocarbon lakes and has this really thick kind of noxious atmosphere on top of it. But underneath all kind of that goop, we think there actually is a nice ocean of liquid water. So under these hydrocarbon lakes, we think that there's an ice layer, and then below that ice layer is one of these great water layers. When we think on the case of Titan, it's sandwiched between two ice layers. So next slide, please. We're going to go back and explore Titan with the Dragonfly mission, which is currently being built at the Applied Physics Lab in Maryland, and this is going to launch in about 2028. So we're so excited for this octocopter mission that will actually take advantage of that thick atmosphere to fly across the surface of Titan, landing multiple times to sample that surface. So this is going to be so cool.
So cool.
Yeah. And so then next, another world in the Saturn system that's really cool, next slide please, is Enceladus. So Enceladus is this little tiny moon, but we think, like Europa, it has this ice crust at the surface, a liquid water ocean, and then a rock layer. And one of the cool things about Enceladus is that we actually found during the Cassini mission, we saw active jets that were erupting from this south polar region. Next slide, please. And so these jets, you can see in this little movie, this material just being thrown out into space, and this is predominantly water vapor. So this is kind of like your plume is venting into space. And so Enceladus is another target that we're hoping to explore in the future. You'll hear more about that in another minute. But next slide, please. I want to head even further out into the outer solar system. So we have other worlds. We have like Mimas, which is another moon of Saturn. We have Ariel in the Uranus system. We have Triton in the Neptune system. And then even some of those minor planets like Ceres and Pluto. And so next slide, we're going to explore the moons of Uranus. So moons like Ariel, Umbriel, Titania, and Oberon. These are worlds where we've only seen them in a single flyby by the Voyager spacecraft in the 1980s. And so we don't know that much about these, but some current models show that these moons too could have a thick ice layer at the surface, and there could be an ocean of liquid water under that ice. And so next, please, these worlds are going to be explored in the future by the Uranus Orbiter and Probe, which was recommended by the recent decadal study from the National Academy of Science as the next flagship level mission that NASA is going to build after Europa Clipper. So we're really excited to get to explore these ocean worlds, as well as other exploration in the future.
You're going to have your work cut out for you. It's an exciting time to be at NASA. Let's bring Lawrence back again with some more audience questions for Cynthia.
Thanks, Greg. Christine Shaw on YouTube asks, how do you know that there's water under the methane lakes on Titan?
That's a great question. So it's more theoretical. It comes from studies of the interior structure using gravity measurements. So similarly to how we know that there's a layered structure on Europa, this is from the very slight deviations in the trajectory. When a spacecraft flies past one of these moons, we can use that to map out the interior structure. And so we can basically get a layered structure with density with layers. And so this is some of the evidence for how we think that there's an ice layer, and then there could be a liquid layer beneath that on Titan. We'll have to go back to really look for sure.
Let's do one more if we have another question.
Definitely. Jordan Fran on YouTube asks, what kind of things could Europa teach us about our own oceans?
Oh, that's such a great question. So our oceans on Earth, they're exposed to this atmosphere, but there's things that are very similar to the ocean on Europa that's sandwiched under this ice layer. And so one of the things that we look at is ocean circulation. So there's models of the circulation of the oceans on the Earth. There's places where the ocean can convect, so that's where it moves kind of up and down in sort of a circular motion. There's places where it's stratified, so where there's this kind of layered structure. And we have models too of how the ocean on Europa might be able to move and flow, so places where there could be convection as well. And so by modeling Earth's ocean, we can learn more about Europa, but Europa could also be an example of a kind of configuration that it's possible the Earth had early in its history. There's a theory called the snowball Earth theory, which is that there was a time in Earth's history when maybe the oceans were all frozen over. And so at that time, Earth could have actually been kind of like a Europa. And so by studying how Europa is now, it's possible we could learn more about what Earth was like back in its past.
Fantastic. Thank you both. Now let's welcome back robotics technologist Dr. Benjamin Hockman. Ben?
Hi, Greg.
Hello. Welcome. With orbiters such as NASA JPL's Europa Clipper and ESA's JUICE mission investigating these celestial objects from space, what might be the next stages of exploration?
Yeah, it's something I think about a lot, and Cynthia just gave you a great overview of just how abundant ocean worlds may be in our solar system, and indeed throughout the universe as we see more exoplanets that have Jupiter-type systems. But the question is really where to go next, and while all of these bodies are fascinating in their own right and have interesting scientific questions, if we want to really get to the heart of, are we alone in the universe? Is there other life even in our solar system? There's really two moons that stand out in particular as promising candidates for next steps. If you go to the next slide. That would be Europa and Enceladus, which Cynthia just talked a little bit about. Not only are they ripe with the building blocks of life, the time, chemical energy, water, and chemical elements, but they also have relatively accessible oceans. Both of them have fairly young surfaces, which give us some indication that they actually could have active ice shells on top of these oceans, which might act to facilitate transport of material from the ocean up to the surface on certain timescales. In the case of Enceladus and potentially Europa, we actually see active plumes being shot out of this ocean. And some of that material falls back onto the surface, which is a really interesting opportunity to interrogate for signs of life.
What mission concepts might we see next?
Yeah, great question. So at JPL and NASA, we're always thinking about the future, and we're always trying to marry our technology that we have that's always evolving with our scientific ambitions, right? And so in the case of ocean worlds, we really want to get closer. We've flown by a lot of these. We've certainly imaged them from a distance. But in the case of Europa and Enceladus, we really want to land on the surface. And while a number of mission concepts have been studied, the recent decadal survey that Cynthia mentioned really had two main contenders for flagship-style lander concepts. If you go to the next slide. One of those is called Enceladus Orbalander. Now this would, as the name suggests, be a mission to Enceladus, which would first have an orbiting component to characterize Enceladus from a distance, potentially sampling the plume as it flies past the body, and then ultimately land on the surface where it would conduct a couple-year-long investigation of the surface. It would land close to these active geysers so that it could scoop up that material and put it into a suite of onboard instruments inside. It also has this interesting funnel on it, which if you've ever been in the snow and stuck your tongue out to try to catch a snowflake, very much a similar concept. It's trying to actually actively capture that snow so that it could analyze it. On the next slide, you'll see the case for Europa, which is a mission concept that JPL has studied a lot. And in this case, this would be a couple month-long mission due to the harsh radiation environment in the Jupiter, because Europa is very close to Jupiter. But it would also have an arm that could scoop this fresh material from the surface and put it into onboard instruments for detecting biosignatures and signs of life.
I imagine the folks who plan and study these missions cannot wait to swim around in those oceans. How might the progression of ocean world exploration play out?
Yeah, and this is something I get really excited about. If you go to the next slide, it turns out this is a topic that scientists and engineers have been engaged on for a number of times, and we've really tried to systematically think about how the progression of ocean worlds exploration might play out in the future, which mirrors a similar kind of exploration paradigm that we had for Mars, where first we flew by, then we orbited, we sent some landers to prospect the surface, and then ultimately rovers of different flavors and even helicopters. In the case of ocean worlds, we're going to go down. So in addition to the orbital mission that Europa Clipper is going to do in future missions, there's a landed component, but then instead of roving out, we actually want to go down into the ice shell, study the nature of the ice shell itself, and ultimately penetrate into that ocean where we can explore a potentially active ecosystem where life may exist today. So if you go to the next slide, I'll walk you through a mission concept profile of what that might look like, where this shows the initial phase, which is very much mirroring what Europa Clipper will start to do in a month or two, where it launches from Earth, does a fairly standard tour around the solar system to energetically transfer to Jupiter, where it would orbit around Jupiter for some time before getting into a European orbit. Now, if you go to the next slide, To actually land, we need rockets. In the case of Mars, we can use entry shields and parachutes to slow ourselves down. There's no atmosphere on Europa, so we have to fire our retro rockets to slow the orbital velocity of the vehicle down, and then perform something of a sky crane type maneuver to deposit a lander on the surface. We call this deorbit descent and landing, as opposed to entry descent and landing. Next slide. And then finally, yeah, what do we do on the surface? So this is a very cool artistic sketch of a lander, which itself would have a suite of instruments and onboard scientific investigations, but crucially would also have a deep subsurface access drill. And this is where the concept of a melt probe or cryobot comes in. These are nuclear-powered probes that use the waste heat from an onboard heat source to essentially melt through the ice shell. And while that happens slowly, but consistently throughout a couple years, it eventually will be able to penetrate kilometers of ice and breach into the ocean where it might detect these alien microbes.
Wow. Can you tell us how a cryobot could work and what kinds of scientific instruments it might bring with it?
Yeah, so go to the next slide. So the cryobot is actually a fairly simple vehicle in principle. It's a cylindrical vessel, sort of like a drill, and at its heart there's a nuclear power source. Think of it sort of like a thermal battery. Then you have a series of pumps and fluid channels within the probe to distribute that heat around the vehicle. Just above the nuclear power system, you have the payload. This is really where all of our scientific instruments would be. These would be instruments that would potentially look out into the environment through cameras or other optical means, looking into the ice and then ultimately into the ocean. But also a wet lab, basically instruments that could ingest liquid water from the ice that's being melted and eventually the ocean for sampling and analyzing on board with things like microscopes. And then finally, at the back end of the vehicle, we need a method to get all of this interesting data back to Earth. So the cryobot actually has to carry with it a tether that pays out from the back of the vehicle, from which it can maintain a continuous communication to the lander, as well as a backup wireless channel. So it would deploy a series of wireless transceivers that would essentially propagate the signal back through the ice to the lander. Now, to give you a really cool illustration of what this mission might look like, go to the next slide and I'll walk you through a very cool animation. So after about a 5-year cruise and journey to Jupiter and the Europan system, we would deorbit from Europa and deposit this lander on this very cracked and icy surface. Now, we don't know exactly what it looks like, but it will be very interesting. So in addition to its onboard science on the lander would deploy this cryobot and put it in contact with the surface where it would start its journey on its couple-year descent through the ice shell. It would do science along the way, and after it gets a few meters below the surface, it would deploy this electronics module that acts as the communication relay back to the lander. As it descends, the wireless signal weakens, so it has to deploy a series of transceivers or repeaters to boost that wireless signal. And also throughout the ice shell, we expect we may see some hazards or cracks, voids, rocks, things of that nature that might be a challenge for the cryobot to penetrate through. So we also have a forward-looking sensor suite that can detect objects ahead of it and a series of thermal maneuvering systems so that it could actually steer around those things. Eventually, it would breach into the ocean, where it would continue its science investigation that's been done throughout the ice shell in the ocean. And while the vehicle itself will remain anchored at the location of the breach into the ocean, it may also be able to carry secondary vehicles, such as this two-wheeled, buoyant under-ice vehicle we call Brewy, which could be deployed from the cryobot and extend its reach so that it could really rove around or swim around in the vicinity of the cryobot. And yeah, really look for those alien ecosystems that we're dying to learn about. So I really like this, this concept, basically roving upside down under Europa. Now, ultimately, we need that data back, so this just illustrates how the communication chain would work, where the signal is sent over the tether and wireless repeaters all the way to the lander, which would then relay that signal either to a relay orbiter or directly back to Earth, where we can finally discover whether Europa is truly inhabited.
That is remarkable, Ben. I know it's a concept animation, but the cryobot really seems like the stuff of science fiction. Is this an entirely new field for us?
Yeah, well, it's certainly an ambitious mission concept, and while it's pretty fundamentally new in a planetary context, actually drilling through ice is fairly familiar here on Earth. If you go to the next slide. It turns out that we have a lot of ice here on Earth, and scientists of different types have been drilling through these ice shells, glaciers, ice caps, Antarctica, for actually over 100 years, with ice drills of different varieties, which provide the technologies that we can pull from for our planetary exploration. These two images are interesting ones that I thought illustrated our deep history. So on the left, you see a very primitive ice rig from a couple of German scientists over 120 years ago, drilling in the Austrian Alps. And on the right, these are two German monks, actually, that pioneered this class of ice probes we call Filbert probes after their name Filbert, which importantly pay out the tether from the back end of the vehicle so that it can remain frozen within the ice. This is the type of probe that we envision sending to, as a cryobot, sending to Europa or Enceladus. And we can pull a lot from these technologies to basically develop the system, albeit there's still several technologies that we have to develop for Europa.
I'm sure. We saw one example of an oceanic explorer in the video you showed. What kinds of other scientific payloads might the cryobot deliver to investigate these oceans?
Yeah, that's a great question. So the primary scientific instrument suite, we call it, would be a suite of different instruments, would actually be on board the vehicle. But we have been dreaming about a number of different roving or exploration vehicle concepts because of our experience in Earth's oceans. We've been exploring Earth's oceans for a long time as well and have developed a number of vehicles. So if you go to the next slide, you saw this cute little buoyant under ice roving vehicle called Brewy. That might be a way to actually drive around on the underside of the ice. Next. This is a concept called SWIM, developed here at JPL, whereby a number of smaller vehicles might swim around in the vicinity of the cryobot in order to map out the local area and provide important context for the science that the cryobot's taking. Next, you could also envision much more capable vehicles. This is a platform called IceFin out of Cornell, which has a ton of instruments on board and can actually swim around a much more distant from where it breaches into the ice. Next, Woods Hole Oceanographic Institute has been exploring Earth's oceans for decades. This is one of the concepts for their very deep ocean exploration vehicles, kind of like the vehicles that James Cameron went on to Challenger Deep some years ago. And next, Stone Aerospace has been developing a number of underwater cave exploration robots, which are similar in nature in terms of the kind of autonomy and agility they need for exploring under the ice shell. And finally, next, here at JPL, we've been developing a number of platforms. This one's called IceNode. This is sort of, you can think of it like an upside-down hopper. So it has a buoyancy control system that allows it to sink and float, and a series of legs that can kind of anchor to the ice as it floats around to really probe up close what's happening at that ice-ocean interface. And next slide. Yeah, this is really the dream shot that I would love to see, where a cryobot breaches into the ocean. It's just full of life. And if you've ever seen any documentaries of deep sea exploration, you have seen the kind of incredible creatures that we have in our own oceans on Earth. You can only imagine what the oceans of Europa and Enceladus might hold in store.
It's all incredible, and I hope you get to do every single one of these missions. Let's bring Lawrence back, because I'm sure we have a million questions. My co-host, I imagine you are just chock-a-block with new questions for Ben.
We have a ton of great questions, and a lot of questions that are really focused on engineering. Marcelo on LinkedIn is interested in learning more about the type of fuel and energy sources that are used in these spacecraft. Can you talk through that in a little bit more detail?
Yeah, as soon as we get past the Jupiter system, we really don't have a lot of solar energy to pull from. Solar panels get just tremendously inefficient at those distances. So all of our spacecraft to distant planets and moons, Saturn and beyond, have all relied on what we call radioisotope thermoelectric generators, which you can think of as sort of like a thermal battery. It's an isotope that decays and generates heat. Some of that waste heat is converted into electricity to useful energy. So they have powered our spacecraft for decades. And in fact, Voyager is approaching its 50th anniversary of a fully functional RTG that's still working to this day. So they're one of the most reliable technologies we have. Now the cryobot would have one of those on board. It would be a little bit different because instead of rejecting its heat to space, it would actually utilize that waste heat through a series of onboard pumps and fluid channels to direct it to melt the ice. So we're actually trying to utilize the waste heat from that RTG.
Great. Let's bring Cynthia back into the mix for some more audience questions for both of our guests here.
Awesome. We have a great question for Cynthia. It's from Rachel Brockman on YouTube. And Rachel would like to know, Cynthia, what is the rust-colored material on the surface of Europa? Where does it come from?
I wish I knew. So that's one of really the big mysteries. We know that from our compositional data, we know that the vast majority of Europa's surface is covered with water ice. But there are these places that are covered with kind of a reddish, brownish, sometimes yellowish, non-ice material. And those regions are often associated with places where it seems like the subsurface liquid ocean has found a way to the surface. So if you picture a picture of Europa, like the one behind me, you have places where these long cracks and ridges seem to have this reddish color. And then these places that look kind of like icebergs where the surface has been broken and disrupted also have that same color. So that gives us evidence that this coloration is associated with material, we think, that's come up from the subsurface ocean and made its way to the surface. And we think from our compositional measurements from the Galileo spacecraft show it looks like it's some kind of highly hydrated salts. So maybe it's hydrated magnesium sulfate or sulfuric acid. So materials that have a lot of salt composition, but they're also mixed with a lot of water.
Cool. Thank you very much. And a question for Ben from Empty Void on YouTube. They would like to know if NASA has partnered or will be partnering with any Antarctic research bases to test this type of equipment. Can you talk a little bit about how we're able to test this type of equipment and these types of instruments in the field?
Yeah, absolutely. Great question. And yes, is the short answer. We partner with a lot of different institutions that have expertise not only in field locations, but in different technology elements. So NASA is always partnering with different institutions to pull the best minds together to accomplish these missions. But certainly, Earth is full of analog research sites that we might visit to study this kind of mission profile. We have been doing missions in terrestrial glaciers that are of warmer ice, up on Greenland summit, which has a few kilometers of ice, and certainly Antarctica is really the holy grail because it has a lot of subglacial lakes where we could actually test the ability of the cryobot to not only drill through the ice, do its scientific investigation, but breach into that ocean. And institutions like NSF have been very helpful partners in orchestrating those kinds of field sites, and we're always collaborating with scientists to test both our technology and ask new interesting science questions along the way.
Awesome. I have a question that might fit for both of you, but Ben, maybe you want to take this too. Matt Pike on YouTube is interested in learning more about missions to the outer ice giants. Do you want to talk a little bit more about how we might be exploring the moons of Neptune and Uranus?
I think I might pass that to Cynthia since she knows a lot about
Sure.
Uranus orbiter and probe.
Yeah, so the main mission that's on the books right now is this Uranus orbiter and probe mission. And so that's a mission that was, like I said, it was listed by the recent decadal survey from the National Academies of Science as the next flagship level mission that NASA should consider. And so the main components of this mission, like the name says, hopefully we'll come up with a better name than Uranus orbiter and probe. But, it's like it says in the can. It has an orbiter, so you would orbit Uranus. It would have an atmospheric probe that would actually descend into Uranus and be able to study an ice giant from the inside for the first time. We've brought a probe out to the Jupiter system before. The Galileo spacecraft actually had an atmospheric probe that went down into the atmosphere. And so we want to do something similar in the case of Uranus. And then the spacecraft itself, it would have multiple flybys of Uranus, and on each flyby you could use your remote sensing payload to observe the giant, the ice giant planet itself, but also its series of moons. And Uranus has a great set of really puzzling moons, many of which we think could have oceans. And so we're really excited to see where this concept goes. So this is still in the very early stages of study. And so while we know kind of the broad shape of this mission, that it'll orbit Uranus, it'll have remote sensing instruments, and it'll have an atmospheric probe, we don't really know the details yet. So stay tuned on that.
Thanks, Cynthia. And we do have one for Ben from Rachel Puckett on YouTube. Out of all of these really cool futuristic robots, which one is your favorite and why?
Oh, geez. Oh, well. That's like asking me
all your
to.
children,
Yes,
yeah.
exactly. That's like asking me to pick between my children. Yeah, I guess I assume she's meaning about these ocean exploration vehicles. Of course, most of my mental energy goes into just how to get this drill working in the first place, this cryobot. So I sometimes let myself dream about the kind of vehicles we will deploy under the ice sheet. And certainly, the farther we can rove, the better. I mean, the seafloor of Europa is deep. It's 150 kilometers deep. So with European gravity, that's about the same pressure as the deepest of Earth's oceans. And we have sent vehicles to those depths before. So in my wildest dreams, I would love to have a robotic vehicle that could really rove, map, and look for things like hydrothermal activity at the seafloor of Europa. Go way beyond where the cryobot breaches into the ice and actually study the seafloor where a lot of these habitats might exist.
Awesome. And I think we have time for maybe one more, Greg, for both of them.
One more, Lawrence, absolutely.
All right, one more. And it's the same question, and we're going to toss it to both of you. And Cynthia, maybe you can start it off. But what inspired you to get into this field? Can you talk a little bit more about your journey, your background?
Yeah, so I was always interested in science, and really in high school, the Voyager spacecraft was flying past the Neptune system in the late 1980s, and as it flew past Neptune, there was a great live feed. This is back in the dark ages, so there's no internet. And so, if you wanted to see something, the science team had to physically come to JPL to see the pictures as they came in from this flyby. So here's the science team, including, Carl Sagan, who was, the giant of the science field in the day. And so he's here at JPL in the control room, and they had a live feed from this on cable television, so on PBS. And so I persuaded my parents to let me stay up. It was called Neptune All Night, and it was literally all night. They had a live feed from this control room, and I stayed up all night with parental permission, and I was just obsessed. And so here are these scientists. Here's Carl Sagan, and he's there, and I remember these pictures were coming in from the moons of Neptune, and Carl Sagan looks at one of these, and he says, "Wow, I have no idea what that is." And that was my moment. It just struck me that there are places in the solar system where human eyes have never seen before. We've never observed them. And there's still so much to be explored. There's still things that even the greatest scientists of the time had no idea what was going on. And I was just hooked. And so, I'm so thrilled, decades later to find myself here at JPL anticipating those new pictures of Europa that we're going to get from the Europa Clipper spacecraft.
And for me, I had a similar journey. I'm a space roboticist now. Before a space roboticist, I was just a roboticist, and before that, just a tinkerer, really. So growing up, I would always take stuff apart, put it back together, build stuff out of Legos and Kinects, and I've always been sort of a tinkerer and figuring out how to make new things, do things that I don't have to do or have never been done before. And so in the academic line, that married very nicely with things like math and physics and the sciences, where I could actually use theoretical tools to design new things. And so I went up through the engineering route through high school. I loved math and physics. My space journey kind of took a parallel path. I grew up in Delaware, which is kind of near a lot of metropolises. Not a very dark sky, so not many opportunities to see just the sheer wonder of the sky. But I do remember distinctively a family trip we took out west to Yellowstone National Park, and one night just pulling over to the side of the road, and I had no idea there were so many stars in the universe, and what I was looking at was just a small fraction of that. And so that really set me on a journey of curiosity in the space domain. And so I had been pursuing this journey of building things, mostly terrestrial things, and just this fascination for space. But it wasn't really until I went into graduate school in robotics where I met a professor that was working with NASA. And they had an interesting research project that they were developing with JPL, which was a hopping robot for exploring asteroids, of all things. So that ultimately made a part of my graduate career. And then I came to JPL after graduate school and have worked on all kinds of missions that marry my passions for space and robots.
So inspiring. Well, my friends, I'm afraid that is all the time we have for tonight. I'm so sorry. I could listen to this. I could listen to this for hours. Thanks to all of you for those fantastic questions, and to my terrific co-host Lawrence. Always great to have you on the team. Thank you. Thank you to our special guest speakers, Cynthia and Ben, for inspiring us with your expertise and passion. Thanks to our amazing social media team for juggling our online presence behind the scenes, and of course to our incredible audio-visual team for making all of this happen and for this gorgeous set. And finally, a special thanks to all of you viewers for being passionate about NASA JPL's work and for tuning in tonight. It is an honor to help share what we do here at JPL with you, and we are grateful for your support. Be sure to join us for next month's Von Karman Talk as we learn about JPL's new Deep Space Optical Communication System, or DSOC. It's going to be cool. Until then, remember, this is your space program. Be involved, stay curious, and hooray for science. Good night, everyone.